Now, we have two presenters. All right. Sharifah Farah, binti Syed Yusoff. Another one is Dr. Wong. Okay. For this session, we're supposed to have 3 presenters, but anyway, 2 turned up. So we have a lot of time. Okay. Presenter has a lot of time, and the audience will have a lot of. We can ask questions. Okay, many questions, of course. Okay, we can discuss a lot because we have ample time. So okay, the first presenter. Okay, the first presenter is Puan Sharifah Farah binti Syed Yusoff Alhabshi. She is a PhD student during the 3rd semester in UKM. She had a degree in actuarial science, okay, and from UKM, and she got a master from Macquarie in the area of actuarial practice. All right, and she is an associate for the Actuarial Society of Australia, and she'll be talking about risk characteristic of aggregate discounted claim with copula, dependent Weibull interweighting time. Okay, so this topic is more on copula and also talking about risk characteristics. So, Puan Sharifah, are you ready?
Yes, Prof.
Okay, so please welcome Puan Sharifah Hafsah, Farah Syed Yusoff Alhabshi for her presentation. Okay, please. Okay. So you can start now.
Is the slide presented? I have shared the slide.
Yeah, yes, it's on the screen now.
Aku tahu dia nak suruh aku ambil apa tu, nak suruh ambil channel. Aku kan tak nak ambil sebab aku kerja aku macam ni kan. That's why aku tak ambil sebab benda tu komitmen setiap bulan kan. So tak ditanya aku income tu penting. Apa tujuan kerja dan macam tu. Of course kan, untuk saving dan untuk beli apa yang kita nak. Macam tu lah, etc. Lepas tu sebab
Okay, Assalamualaikum. Can everyone hear me?
Yes.
Okay, and the slide is, I have presented the slide. Is it there?
Yes, yes.
Okay, thank you. Thank you, Prof. Okay, Assalamualaikum and a very good morning to the moderator, professors, associate professors and doctor, and to all the participants. Okay. Okay, this presentation will be very memorable. It is my very first virtual presentation I ever had. I'm keen to share some of my research output and looking forward to gain some constructive input to improve on my PhD studies. If the slide is missing or you can hear my voice, please just let me know, okay? Okay, my research is on risk characteristic of aggregate discounted claims with copula dependent and Weibull interweighting time. Okay, I shall start my presentation with some brief introduction. Okay, the primary objective of an insurance company is to ensure that they can pay the promised obligation as well as to remain solvent in the business. This can only be achieved by managing effectively its surplus process, so by charging appropriate premium, which will then guarantee adequate reserve and capital requirement to ensure solvency. Hence, they need to adopt a good aggregate discounted claims model for proper estimation. We will first look into the past work of the moments derived from the aggregate discounted claims model. The first few studies were seen in Lever and Garrido in 2001 using renewal theory argument and Laplace transform, while Zhang in 2004 used a different martingale approach. to obtain the aggregate discounted claim. Both work assume independent assumption in their model. Hence, Burgess et al. 2011 and Wu and Cheung 2013 are among the first to derive the mth moment of aggregate discounted claim using the Laplace transform and relax the independent assumptions through copula. Mohammed Ramli and Zhang 2014 extended the work by explicitly finding the Newman series expression and numerically solve the moments by assuming claim arrival following a Poisson process. The studies mentioned in the previous slide illustrated the use of Poisson count model to represent the event occurrence. The Poisson counting process is commonly applied due to its simple corresponding exponentially distributed interclaim arrival time. However, the counting process is only adequate if the data satisfy the restrictive assumption of equidispersion, in which the variance of the data is equal to its mean. However, this is no longer varied if the data or if the arrival of claims varies from what is expected, which is commonly applied data analysis with a heterogeneous population. Hence, a different count model should be used to allow for this variation in the data set to model the aggregate discounted claims. Everyone can still hear me? Yes?
Yes,
Yes,
very clear.
okay, so thank you. Sorry, it kind of awkward because I feel like talking to myself. Okay. The
Sorry,
Weibull count. Yeah.
sorry, Farah, can you open the video on your
Oh,
video?
okay. So will it affect this slide? No.
No. Can you try first? Yes. Okay. It doesn't affect your slide.
And the slide is also there.
Yes.
Okay, thank you. All right, the Weibull count model as seen in McShane 2008 generalized the Poisson counting process to allow for over-dispersed and under-dispersed data set. And they also nest the commonly used count models such as the Poisson and the negative binomial. The Weibull count process has also been applied in a few recent studies in different fields, such as to model the goals, a football match, and to also model the unexpected random shock that lead to the breakdown of many engineering systems. Motivated from the past papers, we would like to develop the aggregate discounted claim model under this Weibull interweighting time, and we would like to also apply the copula to model the model to allow for dependency between the interweighting time and its subsequent claim amount. We would like to illustrate the result based on a real insurance data using the New Zealand catastrophic historical data from 1968 to 2014, in which we will fit the aggregate discounted model on the data set and estimate the parameter estimation and also the best fit copula, as well as the dependency between the marginal into the model. And after using the fitted parameter, we would like to run the Monte Carlo simulations to obtain the moments, the value at risk, and also the premium. We will then compare the result for both Poisson count model and Weibull process under this analysis. This is the proposed claim model in which we define the aggregate discounted claim model ZT. All right. The counting process NT follows a Weibull count process, and XI is a non-negative random variable representing the claims amount occurring at time Ti from I1 to up to the NT counting process. And the exponential negative delta T here is the discount factor, and the delta here is assumed to be deterministic. From the figures on the right, you can see that the time elapsed Okay, between the claims arrival is called the inter-arrival or inter-waiting time, WI, which follows the Weibull distribution. So we have WI from T0 to T1, and then we have W2, which is from T1 to T2, and up to the Tn. The proposed Weibull count model in our work was derived by McShane et al. 2008, in which they derived the probability distribution of the number of events occurring by some time t when the inter-arrival time follow a Weibull random variables, which is derived by a Taylor series expansion and named the count process as the Weibull count model. The mean and the variance of a Weibull count model with shape parameter lambda and scale parameter beta is as in the equation on the right, where n denotes the number of events that occur in the interval 0 to t. So this count model will be used in our model of aggregate discounted claim. The dependency of xi and wi, we know that the independent assumption, as heavily covered in classical risk modeling, may no longer be appropriate in modeling the risk insurance portfolio. Hence, we want to relax the independent assumption between the interclaim time wi and the subsequent claims xi. A copula will be used to capture the dependent structure between these two marginals via the joint PDF of this equation, where this copula function is the PDF of it. Copula is a convenient way to model any joint distribution because we can model the marginal distribution of each variable by itself and link the copula, and copula will link this into a joint distribution. So if we have different marginal distribution, we can model it itself, and then we use the copula to join the link, the dependency between this marginal distribution. To illustrate the model with real data, we fit the aggregate discounted claim model using New Zealand catastrophic historical data, in which the data included is the cost of claim for XI, and the date of event is used to come up with the data of interwaiting time. We fit the aggregate discounted claim model and estimate the parameter of the fitted distribution of the claim size and the interwaiting time, as well as we will be fitting the dependency between the marginals using the maximum likelihood estimation method. And we will choose the best fit distribution using AIC, AKX informations, Bayesian information, Kolmogorov-Smirnov test, and also the Anderson-Darling test. The reason we applied Monte Carlo simulation in our studies because past literatures work with explicit solutions that we know it is from transform Newman series, which result in lengthy expression as well as requiring heavy computational capacity. So we use Monte Carlo simulations to compute higher order moments in much shorter period of time from the basic equation of the aggregate discounted claim model. We will perform this simulation to simulate the pair of random vector xi, which is the claim size, and wi, which is the interwaiting time, from the joint distribution of dependent variable, in which the interclaim time wi would follow Weibull distribution, suggested by McShane 2008, and the claim size xi would follow a distribution fitted from the New Zealand catastrophic historical data. And the steps taken in the Monte Carlo simulation is first we would simulate xi and wi as a pair, and we would compute the ti, which is the time from 0 to I, which is also the cumulative of interwaiting time. And then we would compute the aggregate discounted claim from the model. So we would input the xi and ti from the simulated value, and E negative delta 3 is the discount factor in which we use delta as a deterministic point. Let's say we use 4%. And the moment, and after computing the aggregate discounted claim, we would compute the moments of the ZI, which is the simulator will be used to examine the statistical characteristic of the risk portfolio through the mean, the variance, the skewness, and the courtesies of the aggregate discounted claim model. This distribution moment could provide the shape of the aggregate discounted claim and also the location and the variability by its mean and the variance of the value. We would also want to know the skewness, provided the information on the asymmetry of the distribution, and also either the skewness is skewed to the left or skewed to the right. And we also want to know whether the kurtosis of the distribution, is it a heavy or light tail distribution compared to a normal distribution. Next, after obtaining the moments value, we can then compute the premium computation related to the risk insurance portfolio represented by the first two moments, which is the mean and the variance. And under Solvency II standard, insurers need to provide extra capital through the solvency capital requirement to cope with any unfavorable events in their claim experience. So, in order to do so, this standard formula for SCR, solvency capital requirement, is based from two computation, which is the best estimate that you can measure from expected value of the aggregate discounted claim and 99.5% value at risk. Let me move to the results of the analysis. Okay, the first step that we did is we fit the distribution using the New Zealand catastrophic historical data. And table 1 shows that the log normal distribution is the best fit from the result of AIC, BIC, Comograph and Anderson-Darling test with the least value of AIC and BIC and acceptable p-value for KS and AD test. And the estimated parameter that we gain from this analysis is mean log of 1.3597 and SD log of 1.5286. As for the interweighting time in years that we value in years distribution, you can see that from table 2, which is the goodness of it for fitted distribution on the interweighting time. The Weibull distribution produce a better goodness of fit compared to the exponential distribution, which is the case of a Poisson counting process. Since the shape parameter of the inter-arrival time from Weibull distribution can indicate the dispersion of the claims arrival data set, the Weibull shape parameter value here, 0.70015, is less than 1, indicate an over-dispersion of a data set. This implies that the claims arrive at times are vary more than the expected for over-dispersed case. The Clayton, after we fit for the dependency between the claim size xi and the interweighting time wi, we found that the Clayton copula is the best fit for the dependent structure embedded in this catastrophic historical data. The dependence parameter theta, which is 0.32, is equivalent to a candle star of 0.14, indicate a positive dependency. Hence, it implies that would occur following the long inter-arrival claim time, because this dependency will look into the dependency between the claim size and the interweighting time. So positive dependency, which means that large claim amount, xi large, would occur following large claim of wi. So long waiting of claims arrival would result in a larger claim amount and vice versa. The next is result on the dispersion effect on the moments. Here, we use a machine to come up with the 3 dispersion case, which is from the view of under-dispersed dataset, from the view of equi-dispersed and over-dispersed. And as we know, is from Weibull count process, when lambda is 1, it is reduced to a Poisson count process. And the corresponding inter-arrival time for Poisson count process is the exponential, which is similar to the equi-dispersed Weibull, which is the second row on the table in the table 4. So, looking into this, using the best fitted parameter, we want to examine the dispersion effect of counting process. We can see that the equi-dispersed under table 4 and the count process, we can see that the equi-dispersed case have equal mean and variance, while the variance for over dispersed case is bigger than the mean, and for under dispersed case, the variance is lower, the variance is lower than the mean. So in from figure 1, when we plotted the histogram of claims frequency, looking into the number of arrivals within the interval, such as like from what I did is from 0 to T5, we can see that there are higher chances of more claims occurring under the over dispersed case. Okay, more wider spread for the over dispersed case as highlighted in the blue bar. And the claims frequencies are more concentrated, less spread around the mean for under dispersed case, which is for, blue is for under dispersed, which is there is higher chances, there is more concentrated around the mean for under dispersed case. And green is for the over dispersed case, where we can see that there are higher chances of more claims occurring under the over dispersed case as opposed to the other two dispersion. All right. The wider spread of claims occurring under the over dispersed case, as you can see from the green bar, it will produce a more variation in the results with a positive skewness and heavy tail distribution as reflected in table 4, where we can see that the over dispersed case is highest in terms of the value computed from the mean, the variance, skewness, and also the kurtosis, as opposed to the under dispersed and equidispersed cases. Next, we would like to look into the dispersion effect on premium computation, where after we have computed the moments, then we can easily compute the premium. This premium computed is based on the standard deviation premium principle, and both the premium amount and the value at risk differ according to the risk of insurance portfolio, represented by the expected value and the variance of exact-T. Because we have computed according to dispersion effect, we can see that for premium amount, the premium values for over dispersed case, which is the green line here, produce the highest premium amount over the range of across the different theta. Theta here is the dependence parameter. This is consistent with the result obtained in both figures, where insurance need to charge higher premium if their claim experience exhibit an over. So as opposed to the two other different dispersion, which is under dispersed and equidispersed case. We can also look into the dispersion effect on value at risk, as shown in figure 3. We can see that insurers would need to set aside more capital requirement if their claims experience exhibit over dispersion as per the Solvency II capital requirement. And if you look into these two figures, figure 2 and figure 3, I have plotted across a different data, which means I have plotted across different dependency. 0.32 is the one that is being plotted indirect to the fitted parameter from the New Zealand catastrophic historical data. But the other data is the one that I try to plot it across different data to see how it would affect on the value at risk and the premium across different dependence parameter. So both figure 2 and 3 shows that the premium and value at risk are at highest when the claim size and the interweighting time exhibit strong negative correlation. So the negative correlation here is -1. We can see that where the value at risk and the premium amount is at the highest. This is intuitively reasonable, as short interclaim occurrence time followed by large claim will need higher reserve value. As I mentioned previously, that the dependence is between claim size and the interweighting time. So negative correlation means that short interweighting time would produce a large claim. So if there are a lot of short interweighting time but producing large claim, we would expect that we need to have a higher reserve value. And as we can see from the graph, it produced the highest premium and value at risk from the computation. I would like to conclude the presentation by looking into few perspectives. The dispersion of claim occurrence, which is sometimes ignored in plus claims modeling, is actually common in insurance claim data. for any insurance company, charging the appropriate premium is very important, because it is the only way to guarantee that they would have an adequate reserve, adequate capital requirement to remain solvent in business. So the premium amount under the Weibull process would allow for the dispersion effect to be incorporated in the pricing computation. And from Solvency II standard, insurers need to provide extra capital through the solvency capital requirement to cope with unfavorable events if the claims experience is against what they have been compute before this. And this standard formula for SCR is based on the 99.5% value at risk, whose value we can see varies according to how dispersed the data set is and how the dependency between the marginals are. And other than allowing for a faster computation, without the need to examine lengthy expressions via explicit solutions, as we can see from past previous literatures using Laplace transform Newman series, computing via Monte Carlo simulation produce more robust results to higher order moment, and the flexibility to fit to the best marginal distribution and the best fit copula to allow for the dependency. That's the end of my presentation. Thank you for listening. I hope you guys are still listening. My mic is still okay. I would welcome for any questions and suggestions to improve on. Thank you.
So any question from the audience, please? You can turn on your microphone and maybe your video so that you can ask question. Any question? No question? Maybe I ask. Can you hear me, Sharifah?
Yes, Prof.
Okay, because nobody else wanted to start, so I do the starting. Just about the data. How certain are you that for the case of New Zealand catastrophe, the data involved those who get involved with the calamities repeatedly? How certain are you on that? Because when you talk about inter-arrival, that applies to those who face the problem, continuing facing the problem of the catastrophe. Can you talk about the data a little bit?
Okay. The data that I gained from New Zealand catastrophic historical data consists of cost of the claim and also the date of event, which is where I computed the inter-arrival time. So I'm not looking from the perspective of using the generalized count model to come up with the count process, to come up with the count model first, but I use the interweighting time as proposed by McShane. Hence, we compute the inter-arrival distribution first and see whether is it Weibull distribution is a good fit to the data or not. And from the fitted parameter, we can see that under McShane paper on a count model, they have used extensive simulation to see whether this interweighting time could indirectly shows the dispersion of the data, whether it is an over-dispersed data or under-dispersed data or an equi-dispersed data. So from this,
in other words, you don't have the detail on the data. You just assume that the people that are involved in the data set, maybe they do some claim, so they face the catastrophe repeatedly. So because you need the inter-arrival time, is it?
Yeah,
So
because I use the inter-arrival time. Yes.
Yeah, I'm just wondering about, because it may be that some people, okay, whereby the information has been taken by maybe the reported data, maybe they did not face the catastrophe repeatedly. So how sure are you on that? It's just maybe you can allow for certain uncertainty regarding that. I'm just wondering.
Because I don't look into the number of if you look into the count. If you look into count model as a beginning, we will see how many claims coming from the same policy, right, Prof?
Yeah,
But
yeah.
here
maybe
we are
something like
looking
something
into the inter-arrival time, which means that we are looking into the how many claims would arrive after we wait for another claim. It could be a repeated claim for another years, probably like the same catastrophic event happened at the same place for a few years after that. But because we are looking into the how would the interwaiting time would produce the subsequent claims amount after that. So we model the interwaiting time as the Weibull distribution. Then only from that Weibull distribution, we deduce whether it is an over-dispersed or under-dispersed or equi-dispersed case. Because this is actually done by McShane as well, but from a perspective of McShane, he did both, meaning the counting process first and also doing the inter-arrival time process first, and then he measured the difference doing by extensive simulations. He sees that the data or the results that he gained is consistent, which means that the count model that is over-dispersed is consistent with the result from the over-dispersed inter-arrival process.
Okay. Anyone want to ask question?
Or you have suggestions, Prof, for improvement?
No, I'm just wondering. It is interesting topic, but again, you are looking at the case. You say under dispersed, equi-dispersed, and also over-dispersed, and you've been saying that if the data is over-dispersed, then we have a higher value at risk, isn't it?
Yeah.
Yeah. So,
Because
but
of higher spread. Yeah.
it's not surprising because when you have over dispersed, that means the claim will vary so much between the minimum and the maximum. So that causes the value at risk to be high.
Yeah.
Can you consider the case where you allow for certain parameter, dispersion parameter, instead of saying, well, this is over dispersed, this is under dispersed, and okay, this is equi dispersed. Allow for certain parameter in the model. I don't know how.
Because
And
I
how
understand, Prof.
change the value
Yeah.
of this dispersion parameter. What would the result? How would the result change?
From the result that I did before, one is from the fitted parameter from New Zealand catastrophic data, and then when I go into the dispersion effect, I actually try running with different parameter. Under the Weibull process. So there are two actually results there. First is from the fitted parameter New Zealand catastrophic data, where I got a Weibull distribution shape parameter of 0.7 and scale parameter of 0.28. And then I see how it differ from the exponential distribution for that over dispersed case. And then again, I do using a different parameter where I just change the parameter to cover for 3 dispersed case, which is the equi under and over dispersed case. That is for, the parameter is changes according to the dispersion data. I understand, Prof, that when we say seems clear if this over dispersed data would result in higher premium, higher value at risk. But from past literatures for underclaim modeling, for the especially on claims modeling under the Roon process, when they found the Roon probability theory, normally the past literatures, they are using an explicit solution, and also they are comparing that using a simplified Poisson process, and also because they allow for the dependency and they use the simple Poisson process to come up with the explicit solution. Most of the past papers normally would simplify that into a Poisson count process. That is why actually the research is motivated from the past literatures, when we see that if the data comes from a dispersed data, you would actually clearly know that it would have higher value at risk, higher premium would affect the value computed by the insurance company. But however, the past papers, they normally assume a simplified version using a Poisson count process. So my research PhD is somehow we want to try to put Weibull process into the research into the claims model, and also after this we'd be continuing it with the Roon probability theory using this discount process as well.
Okay. Any question from the audience, please? So you're saying that if you were to allow for this Weibull inter-arrival time, then your result will be worthwhile as opposed to consider simpler inter-arrival model, such as the exponential model.
And we want to propose it for the insurance companies usage as well.
Okay. Right. If there is no question from the audience, I think thank you very much, Miss Sharifah Farah, binti Syed Yusoff Alhabshi, for your interesting talk. And shall the audience join me to clap? I did the clapping here. All right. Thank you very much.
Thank you, Prof. Thank you all to all the participants.
Right. Okay. Well, we go to the next speaker. The next speaker. Can you open your video, please, for the next speaker? The next speaker is.
Hello.
Yeah, Dr. Wong.
Hello, everyone.
Yeah, Dr. Wong. Please turn on your
Hello,
video.
Prof.
Yes, hello.
Hello.
Dr. Wong, you around? Okay. Okay, Dr. Wong is a senior lecturer at Institut Sinaran, Sabah. She got a PhD in the area of planning and development economics. Okay. Her area of interest include, among others, public spending, economic growth and development. And she'll be talking about Toda-Yamamoto Causal Analysis, Health and Economy, Evidence from Malaysia. Please welcome Dr. Wong Sin Yun. So can you please turn on the video and turn on your mic? Dr.
Hello,
Wong?
everyone. Thank you, Prof, for the introduction. Okay, let me share my slide with you all. Are you all able to hear me?
Yeah,
Is
I
my
can.
mic working?
How about the
Hello?
others?
No problem, Prof.
Okay, thank you. Okay, good afternoon, everyone. Right, my name is Wong Sin Yun, and today I will be presenting to you all a topic entitled Toda-Yamamoto Causal Analysis between Health and Economy, a Dividends from Malaysia. Okay, now as of today, we know that health status of a population has always remained to be an important issue. And in fact, the improvement of the health status of the population has always remained to be one of the key policies in developing a sustainable development that has been taken into consideration by most developing countries. Now, in our research here, we will be using the life expectancy chosen as the indicator of the health status of population, as we have go through the literature review, and we find that this is the indicator that has been widely used to represent the health level of the population. Yeah, being because that life expectancy measures to us the expected length of life lived by individuals at birth. So it becomes a very good proxy of the health level achieved by population in a certain country. Now, the analysis on the level of life expectancy has an important implication because by analyzing the health status of the population, we wanted to actually find out what are the implications from, let's say, if we want to improve on these life expectancy of the population, will it affect the economic growth, and to what extent is it going to affect the economic growth? And besides that, can it also affect other social economic indicators as well? Now, before we look into our study, okay, let me bring you to the data analysis. Okay? Now, these data are extracted from the World Bank. If we look at these trend here of the life expectancy in Malaysia, we do see, which is indicated by the blue line graph, we see that the life expectancy in Malaysia is experienced a slow and steady increase over the years from 1971 to 2018, which is a very positive sign. But if we were to compare that with the life expectancy that comes from the developed countries, particularly the Asian developed countries, such as Japan, Korea, and Hong Kong, and we realize that we still have a long way to go before achieving the level of a health population as on par with those developed countries. A comparison being made here, we see that Japan and Hong Kong has always been having a higher life expectancy compared to us since back in the 1970s. Yeah, but a look at Korea's data, we see that Korea's life expectancy was surprisingly lower than us in the early 70s. Yeah, but starting around 1987, they started to experience a booming increase to their life expectancy that pushed them up to the level of a developed country, yeah, allowing them to achieve the status of a developed country, whereby their health status of their population has approached the very level of the health status of a developed country. So let's not go too far. Let's go back a little bit on a comparison with the ASEAN countries. Take an example of our neighbor country, Singapore and Thailand. Yeah, we see that the life expectancy of Singapore was over the years has been higher than us, most probably because they have achieved the status of a developed country. But if you look at Thailand's life expectancy, their life expectancy was relatively lower than ours back in the early 70s. But coming up to the late of 80s, they experienced some increase there, reaching to a level which was seemingly very close to our life expectancy. There's a slight fluctuations of the life expectancy. Then after that, there's a slight decrease. But more of the recent years here, as we look into the comparison of the more recent years, which is around 2012 to 2018, yeah, we can see that there is an increase to their life expectancy to a level which is a little bit slightly higher than ours. So perhaps these studying of the trend of these life expectancy of these countries, therefore, is prompting us that there is a need to analyze on how we can actually try to improve on our life expectancy, our health status of our population, to see that if these health status of the population can perhaps could be bringing some significant effect to the social economic indicators, and could the changes in these social economic indicators be bringing effect in trying to improve the health care or the health status of the population, which is what we intend to study in our research. Besides the trend of the life expectancy of Malaysia that was analyzed earlier, our study was also motivated by some of the conflicting findings that was being found in the past literatures, the arguments with regards to the relationship between unemployment and life expectancy, whereby there has been arguments to say that unemployment could be a health hazard. Yeah, and we also understand that some literatures has also argued to say, could it be the other way around? That means because of the health problem that brings to the unemployment rather than the unemployment that is creating the health hazard here. So that invites therefore a need for a causal analysis finding to find out the true causal effect between these two variables. In addition to that, the health income nexus is still remain to be a debatable issue, because we find that many past literatures has always been trying to investigate on the relationship between the health and the income, yeah, the GDP and the health expenditure. So estimation of the association here between the life expectancy with the social economic indicators, especially by trying to find the true causal effect between these variables, will be pretty much very crucial in trying to highlight to us how far is our progress achievement so far, and perhaps in the future to come up with certain policies that may allow us to improve on our health status, boosting us to a level of health level or health status of the population, which is approaching the level of a developed country. And so in this study, we will be using the granular causal. The technique approach here that we'll be using is the Toda-Yamamoto Causal Analysis to analyze and to examine the granular causal association between life expectancy, which is a proxy of the health status of the population, with other social economic indicators, in allowing us to formulate some future public policies that can help to increase the health level of the population. Now, according to an independent commission that was set up by the World Health Organization, the health status should not only be a concern to policymakers in the health sector, but rather it should be a concern to all policymakers. All public policymakers should be concerned with that, which means that if there are any changes to the social economic indicators, which may not be a direct changes to the health status, but changes of these social economic indicators, if they are to have certain causal effect on the health level, changes of these policy can certainly bring improvement to the health level as well, which is why they are suggesting by Marmot 2005 to say that health status is not just a concern to health sector policymakers. That means we're not just focusing on how to improve the health sector. Does not just lies at the responsibility of the policymakers that are under the health sector, but rather it's a responsible of all public policymakers. And so that brings us to the research question, that mainly what we want to find out here is what is the true causal effect between health status as proxied by the life expectancy, as well with the other social economic variables. The study will be using an annual time series data from the period of 1971 to 2018. All the series will be transformed into logarithm form to avoid heteroscedasticity problem. The following is our model specification. Life expectancy has been chosen as a proxy of the health level of the population, with a few chosen socio-economic indicators being the real GDP, which proxies the economic growth, the health expenditure, in order for us to analyze the conflicting findings surrounding the issue of health income nexus, and unemployment rate is also chosen in order for us to analyze, again, to clear some doubts perhaps with regards to the issue of the conflicting findings between unemployment rate and health status of the population, whether unemployment is a health hazard or otherwise. The following are the measurement, the descriptions of the variables, and the sources of where we have extracted the data from. And so, as mentioned, this research will be applying the Toda-Yamamoto causality approach, which is a very efficient method to test the causality approach, as can be used no matter what is the stationary of the data, whether they are first difference, they are stationary at level, or second difference. The following models has been formed. There are 6 models that has been formed in order for us to find out the true causal effect of the life expectancy with each of the social economic indicators: the real gross domestic product, the health expenditure, and employment rate. As I mentioned, all these time series data will be logarithm. It will be performed with logarithm, transform into logarithm form in order to avoid the heteroscedasticity problem. So preliminary finding of our granular causality test has found out the following. Here we see that the p-value is less than 5, signifying that the values are significant at 5%. Okay? And we find there is a bidirectional causality that was found between real GDP and life expectancy. As shown in the following table, a causality relationship exists between flowing from GDP to life expectancy, and likewise, it also flow from life expectancy to GDP. Because the variables that was found, the p-value was statistically significant. Meanwhile, a bidirectional causality was also found between the health expenditure and also towards the life expectancy. Vice versa, life expectancy was found to branchly cause the health expenditure. Meanwhile, as for the relationship between unemployment and life expectancy, we find that unemployment rate branchly cause life expectancy, but a likewise branchly causal effect was not found from life expectancy to unemployment, which brings us therefore to the following discussions and conclusion. A bidirectional causality between life expectancy and economic growth has provided the support to the health income nexus, which was actually in line with some of the findings by Chor 2011, Chan and Davey 2015. The causal relationship found between life expectancy and the economic growth has perhaps suggesting to us that health has remained to be playing an important and significant role in supporting the economy. Only when we have a healthy population, then we are able to have experience economic growth, because these healthy population will be able to contribute significantly to the economy. All right, and of course, a vice versa relationship was found from economic growth to life expectancy. That means when the countries are doing very well, they are able to perhaps spend more on improving the healthcare, which is also ultimately going to improve on the health status of the populations, which is again in line with Chan and Davey finding in 2015. Meanwhile, a bidirectional causality association between life expectancy and health expenditure suggests the following. Government's allocation had a simultaneous cause and effect on life expectancy. Okay? Which means that improvement of the life expectancy, healthcare is able and efficiently able to have certain effect on the life expectancy. Vice versa, life expectancy could have led to the increase or decrease of the healthcare expenditure. Meanwhile, a unidirectional causality that runs from unemployment rate to life expectancy was in line with past studies by Monsef and Majority 2015, Tafran et al. 2020, Sade and Ohemeng 2015, which interpret to us to suggest that it actually provided a robust support that unemployment could be a health hazard. Yeah, because when people are out of job, this can be a very stressful life event, and they may be taking care less of their health because of that, which could lead to health problems, which could lead to health condition. Besides that, people are employed are less sensitive to their healthcare, right? So that will be the suggestion in the interpretation of our findings. Thank you.
Well, thank you, Dr. Wong. Any question from the audience? Any question from the audience? You can just turn on your mic and ask question. Who want to ask question can raise your hand, or maybe write the notes in the chat. Maybe any message from anyone?
Me, Prof.
Yeah. Okay. Please. Can you introduce
Yes,
yourself and then ask question, please?
Hi, I'm Leong, Dr. Leong from UKM.
Okay, Dr. Leong, please.
So actually, I missed this presentation, but I just came in a bit late. But is there a difference between gender, the effect of the effect of this study on gender perspective? So which gender was more affected? I believe it's male, right? Can you elaborate a bit more, Dr. Wong?
Thank you for the
Thank you.
question. Now, because this is a preliminary finding, and so far we have not differentiate in terms of the gender here. Yeah. In terms of the health status, we're just looking at the health level of the entire population without differentiating on male and female.
I
That could
see.
be a good subjective if we consider that for the extension of our study. Thank you.
Thank you.
Any other question? Thank you, Dr. Leon. Any other question, please? I'm just wondering, I'm not an economist. See, I'm used to this idea of regression, and we don't have the causality test. Well, I've never come across this causality test because I'm not an economist pertaining to the subject matter that you have. See, if how would it differ from, let's say, in the regression relationship as opposed to the causal analysis? Say, for example, you are looking for investigating the relationship between, let's say, the one of the variables against another one. So, for example, the log of GDP against the log of life expectancy, and we would be able to see, for example, in the case of regression, simple regression, this is my guess, I'm not doing it, you see a significant relationship. How would this, the interpretation with regard to your work, talking about causal analysis, differ to the interpretation with regard to, let's say, simple linear regression I've mentioned earlier on? So Dr. Wong, please, can you explain to us about it? You are an economist, so you, of course, you know better about all this stuff.
Yeah.
Causal analysis.
Thank you, Prof, for the question. Now,
Okay. Thank you, Dr. Wong. Any question, please? Any more from the audience? You still got a lot of time because we're supposed to have 3 presentation, but we got only 2, so you still have more time.
Hello, I have one question.
Yes, please. Yes.
Yes, I'm Izzat from Department of Statistics,
Right.
Malaysia. Regarding the Toda-Yamamoto causality test, do we have any kind of what we call the forecasting for the future regarding the GDP or for that data? Because when we deal with the time series data, I think we should have kind of the forecasting what will happen in the future, especially for Malaysia. You have any idea, Dr. Wang, for this?
Okay. Thank you. Any more questions?
Thank you.
Anyway, our session supposed to finish at 12:30, I think, because I've given 75 minutes, 15 minutes for each presentation. So 15 multiplied by 3, I got 45 question and answers for each presenter, 5 minutes, and then there will be an additional few minutes more. If you have any question, you can ask any of the presenter. It could be Dr. Wong or Mrs. Sharifah Farah. Any question from the audience, please, before we wrap up?